Very
I think Regression is part of
Have you ever seen?
Just one.
Hi everyone. Hi everyone. So we were left this slide, relation of singular value decomposition and eigenvalue decomposition. Now we continue to finish this slide. I usually go over the references too, because I think references are important. So acknowledgement. Some slides are based on our textbook, Elements of Dimensional Reduction, Manifold Learning, published by Springer. You see that for more information on optimization, refer to my course Optimization Techniques in University of Guelph. Here is the YouTube link for the playlist of that course. And now also the references. So this is the book that I was talking about. This one is the survey for prototype selection. Remember when we were talking about numerosity processing, that we have anomaly detection, we have prototype selection and prototype generation. So this is a survey on prototype selection published in IEEE Transactions on Pattern Analysis and Machine Intelligence, one of the important journals about machine learning in IEEE. And also this one is prototype generation, a survey on prototype generation in IEEE Transactions on Systems, Mans, and Cybernetics. Also, this is my PhD thesis, Data Reduction Algorithms in Machine Learning and Data Science. This is a book on Principal Component Analysis by Joliffe. I think this is an important book. Also, for eigenvalue problem, algebraic eigenvalue problem, you can take a look at this one. And this is matrix computations by Golub and Alone. I think Golub's book is very important on matrix computations. Many people refer to it. So you can use it for different calculations and linear algebra and matrices. Also, the symmetric eigenvalue problem, you can take a look at this journal paper. The history, an early history of singular value decomposition in SIOM review. So it's a review, a survey paper on SVD, which is a good reference. Also, Golub again. Golub was, as I said, was an important scientist in linear algebra and working with matrices. So singular value decomposition and least squares solutions for solving singular value decomposition. And this is also a tutorial paper of ours, eigenvalue and generalized eigenvalue problems, which talks about eigenvalue problems and also relation with SVD. Also, it talks about Rayleigh-Ritz quotient. So Rayleigh-Ritz quotients I didn't cover in this course. I covered in statistical machine learning course because it's not much related to deep learning. But if you're interested, you can take a look at that in the preliminaries on linear algebra in the other course on YouTube. Okay, so now let's go to the next one. So by the way, I asked you all to kindly take a look at the lecture on overfitting and regularization. I hope you have done so. If not, please do it. There is time for it, but please do it. I recorded a 3-hour session on the overfitting, regularization, and overfitting, cross-validation, regularization, L1 normal regularization, and L2 regularization. Take a look at that. That is important for both statistical machine learning and also deep learning. So, it's important for both. And the materials in that section rely on the books, the tutorial lecture of Professor Ali Qudsi, and also the groups of Hasty and Tipshurani, the statistical elements of statistical learning. The other one, also deep learning book by Goodfellow, also talks about that a bit. So now that we have covered the preliminaries, let's jump into neural networks. But we will start with training one neuron, and then we'll go to training one layer. Then we will increase the number of layers. Okay, this is the approach that we are gonna have. Training one neuron. Okay, the neuron and McCulloch-Pitts model. So, what is biological neuron? Our brains have a lot of neurons in it, as you know. So, brains of human, also animals, and these things. So, a neuron is a cell, and it has several things. So, one of them is nucleus, which is in the neuron cell, the core of the neuron cell, as you see in this figure. Here, this is the nucleus or the core. Also, it has some soma, or is the cell body of the neuron containing the nucleus. This is the soma. Also, dendrites. So the branched, the protoplasmic extensions of a nerve cell that propagate the electrochemical stimulation received from other neural cells to the cell body or soma of the neuron. So these are dendrites, and as you see, neurons communicate with each other through the dendrites, but there is a synapse or some gap between the dendrites, and this is a biological process. So they transfer the electromagnetic or electrochemical, I think, electrochemical signals through the dendrites and through the synapse or gap between the dendrites. So this is how it's working, the small gap between the dendrites of connecting neurons, the synapse. And also you should note that how do we learn in our brains? So whenever we learn something, some neurons are fired, and when several neurons fire with each other, the connection between them gets strength. This is how we make paths between the neurons in our brains. And the more we study that subject, or the more we practice that, the stronger the connections between the neurons will be. That's why practice and studying helps memorizing, also better understanding. So that's how our biological neuron is. Okay. So in the previous century, in 1943, the first model of neuron was invented by McCulloch, who was a psychologist, and Pitts, who was a logician. So they said, let us, because at that time computer science was going to grow, and they said, okay, let's simulate a biological neuron computer. Do it. Hopefully we can make artificial intelligence. So because neuron, we know that intelligence comes from neuron in our brains. Therefore, let's simulate that in our brains. And so they proposed something which we are going to discuss in 1943, and it was later named the McCulloch-Pitts model because it was proposed by McCulloch and Pitts. And McCulloch was a psychologist, biological part, and Pitts was a logician, the computer science part. The model had two inputs, or two or several, but initially it had only two inputs and a single output. A neuron would not activate if only one of the inputs was active. So it would only activate if both inputs were active. This is how they were modeling the neuron. And also the weights for each input were equal and fixed. So they didn't train the weights. So it was like this. The neuron was like this. we had two inputs, maybe x1, x2, a w1, w2. There was also something called activation function. And then there was an output, and they weren't training w1 and w2. So these were some parameters, but they weren't training initially. And the output was binary. So because this function was with 0 and 1 was a binary function, which was 0 for x for some, if this signal input to this function is less than 0, and if the input was greater than 0, then the binary function would output 1. Why did they make it binary? Because Pitts was logician. Right? In logic, we have binary logic in computer science, 0 and 1. That's the reason. Also, until input summed up to a certain threshold level, and the threshold level can be determined by where we put this. For example, if we put it here, function, or if we put it here, or if we put it here, right? By the value of the threshold, playing around with this threshold, they could say, okay, I choose my threshold, and when the inputs sum up to a certain level, w1 x1 plus w2 x2 is greater than the threshold, then I'll output 1. Otherwise 0, right? So, and as you see, it's like a logical gate. Which one of you have passed logics or computer science, in computer engineering also, logical circuits and this. So we have several gates like AND, or XOR, these things, not. So these are some logical gates, and is 1 only if both of the inputs are 1, or is 1 if at least one of the inputs is 1. So not negates it. Also, we have other gates such as XOR. So they could maybe model a logical gate using a neuron, by simulating a neuron. And they were thinking, okay, firing a neuron is like 1, not firing it is like 0. Like that. So the formula was like this. O is the output. You can see the figure here. O is the output. And so we have some inputs. For example, we have D inputs. You can see that the D-dimensional vector. And each of the elements of X, X1, XD, so X can be seen as X1, so XD, transpose. I understand that in your mind, you might say, it's very easy. So why are you studying this? We need to study this and become more complicated. This is how it all started. And I think it's very shocking that about 70 years became so much complicated. Started 1943, 1950, 1950, something like that, around that time. Not much time has passed, and we have improved a lot. I know initially it was very simple. So X is a vector, x1 to xd, and you multiply each of the elements by some weights w1 to wd, and then you sum them up. Also, you can have some bias, right? And why do we need bias? Why do we need bias? Why do we need bias? So soon I wanna regress something. Okay, later. Later I wanna using neuron, I wanna regress something. For these data points, the regression would be like this, right? This is a regression line, right? But what if my data is like this? If I don't have any bias, maybe I will regress something like this, because have to pass through zero. But if I have bias, then I can add bias to it, and regress correctly. In electrical engineering, that's called DC signal, or you can, in mathematical language, it's intercept, right? So you need bias or intercept in order to be handled to if the data doesn't pass through zero necessarily. And by the way, these in mathematics, this is called the linear function. But this function is called affine function. This is A transpose X plus B. Okay. A and X might be vector, higher dimensions, but B is a scalar. Sometimes people call this affine function also linear. Sometimes people also call it linear. However, to be more precise, this is affine, this is linear. Affine is a linear which might have some bias too. That's one thing. So this is the reason for bias. And you multiply it with some W0, you have W1x1 to W you sum them up. So this is the sum. And then you pass it through some activation function, F maybe. Can be in McCulloch-Pitts model, it was between 0 and 1, it was binary. And the output would give you the output. So here it is. The output is F of the summation. So we have Wj xj, j goes from 1 to d, and then W0, x0 is 1 because it's bias. Doesn't matter if you set it to 2, then you will learn something to W0 over 2, something like that. So you don't care. And then you also pass it through some function f, or you can also consider x0 to be one of the dimensions of x. So if x is d-dimensional, you can consider it to be d plus 1 dimensional. Okay. And you will have x0, x1 until xd, where x1 is set to 1. You can also do that. By the way, adding fake dimensionality is also useful in computer vision. You go and read the camera models, you do these things. These are good techniques that you might also want to learn. Okay. So perceptron. Hebbian learning. So Hebbian theory is a neuropsychological theory claiming that an increase in synaptic efficacy arises from a presynaptic cells repeated and persistent simulation of a post-synaptic cell. This is, I know it has hard words in it, but in simple words, what does it mean? It means that the first sentence that I said in this session, I said, when we have several neurons next to each other, when we do something, some neurons fire up. Those neurons which fire up together, they will make connection. And the more they fire up together, the stronger that connection would get. Okay, this is what Hebb, I think, was a biologist. Hebb found it, so that's why it's called Hebbian theory. Okay. In simple words, the more two adjacent neurons are activated or fired together, the stronger the connection becomes between them. Okay. Hebbian learning was proposed by Donald Hebbian in 1949 in his book, The Organization of Behavior. So he proposed something named Hebbian learning. Now let's talk about perceptron. These are building blocks of neural networks that we are gonna learn. So perceptron tried to learn by neuron as done in brain. So please note that McCulloch-Pitts, which we covered, didn't learn anything. Thought that it assumed that the weights are fixed, right? Now first person said let it be learned. The first model was Perceptron. By the way, how did they use McCulloch-Pitts? They just randomly tried different ways in order maybe to do something, to do some task. So when you select some weights work for you, right? This is what McCulloch-Pitts did. But Perceptron said, I don't want to try and error. I want it to be trained. Perceptron is the building block of nowadays neural networks. And Perceptron was implemented by Rosenblatt, a physiologist, in 1958 at Cornell Aeronautical Laboratory in Cornell University. So it was for binary classification, only binary. And it was useful because binary logic could do computer operations. At that time, they were mostly AI was dominated by logic at that time. Nowadays, it's a bit different. But at that time, whenever people wanted to design something in AI, they were thinking about logic, or gates and these things. So binary logic could do computer operations. And I think the reason is because computers work with binary logic. Even when we have multiple classes, we can consider pairs of classes, right? If we have 3 classes, we can take class 1 and class 2, class 1 and class 3, class 2 and class 3. So we can train 3 classifiers in order to separate these. Okay, Rosenblatt at first randomly connected perceptrons and changed the weights manually in order to achieve learning. In later attempts, Hebbian learning, proposed by Hebb, was used for learning in perceptron. Initially, it was set manually, the weights, but later Hebbian learning was adopted for learning. In a 1958 press conference, and that's interesting, see the history and you'll maybe you will laugh. In a 1958 press conference organized by the US Navy, Rosenblatt gave a speech about perceptron. And he said how wonderful it is. Of course, whoever proposes something, they will say it's wonderful. So afterwards, because of the excitement that had appeared for his speech, afterwards, New York Times reported the perceptron to be the embryo of an electronic computer that the Navy expects to be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So basically, it said that perceptron can make a human. This perceptron one neuron can make a human, and it can walk, talk, see, write, reproduce itself. I think this is the goal of AI. Maybe if we might not reach it in 100 years, that AI makes another AI consciously. So whenever we can make an AI module, it's conscious of itself and also makes another AI consciously, then I think AI is done. Okay, because we have made a human. Then, so that at that time, they were very excited about it, and I think they thought they have solved AI. No. Okay. So this is perceptron, and you see some difference. So you see this part, which we didn't see in McCulloch-Pitts model, which is for training. And as you see, it's like a feedback. Have you passed any control course? Like linear control? No? Okay. In control, we have some function or some plant, some system. It has some input, some output. And also we have maybe C. Okay. So we have some input. It goes into the function. It is, so assume it's X. X minus, let it be Z. So x minus here we'll have x minus z, right? X minus z goes into f. And what do we have here? F of x minus z. What is z? Z is c of f of x minus z. Okay. And each of these have their own mathematical formulation. You can model it using Laplace transform and these things. Okay. And they try to design C in a way that they can control F, so it doesn't overshoot, for example. They control its overshoot. For example, if you input something, X is like assume it's like a step. What is a step? For example, you click on the button. Button was off, suddenly turned it on. So it's like a step signal. Goes, if you don't control F, it will overshoot. Then you will have some C in order to control F, control the behavior of F. This is what control systems do. And they design C in order to do what they want. And as you see, it has a feedback. It has a feedback, right? And it is a negative feedback. If it is a positive feedback, it's usually unstable. I'm sure that you have seen positive feedback. So in negative feedback, an example of negative feedback in real life is that you go to shower and you take one of your hands under water and one of your hands just turns, is it called? The knob, yeah, turns the knob in order to make it see how cold it is, how warm it is, right? And you're just controlling. It's just feedback is your body, your brain. You turn it. If it is too cold, you make it a bit warm. If it is too hot, you make it a bit cold. This is negative feedback. What is if it was positive feedback? If your brain was a positive feedback, then you would ruin your water temperature or your hand. If it's cold, you make it colder. If it's hot, you make it hotter. If it is hot. So, but in real life, we have seen positive feedback. Can you give me some examples of positive feedback that happen in real life? Just echo. When you have a microphone, sometimes when you say something, it echoes and goes up and up and up until you can't hear it, right? It becomes very noisy. Sometimes when you say something small, it becomes very large. So this is positive feedback in the system. Again, we can have control system in order to control that, in order to avoid that echo. So this is what they do. And as you see in here, also in Perceptron, we have feedback. We have feedback in order to training. Even back propagation, I think from its name, you can see it's kind of a feedback, back propagation. You're back propagating it. When to start. You can see it as a feedback. Okay. So here we say we have the McCulloch-Pitts model, however, it's improved. The output, we have some feedback, and this Y is the target. So you have the target labels for classes, whether it's class 0 or class 1, right? So you have that, you want the output to be similar to Y. That's why you have subtraction between them. Y minus O or O minus 1. Y doesn't matter. Okay. Y minus O goes to some Hebbian learning, which we'll see, and then it updates the weights. Okay. And the activation function in Perceptron here is again binary 0 and 1, because at that time logic was important. So this is Hebbian learning. If each weight Wj is updated by Wj, so this means update here. Wj plus eta times yi minus oi. So this signal here is y minus o, right? Yi minus oi times xij, and this eta is a positive number. Is called the learning rate. This is a hyperparameter. Xi, let it be x. So xi, what do I mean by xi? Means the ith data point, because we might have several data points, right? ith data point is a vector. Xij means the jth element of xi, right? xi1 to xid. Ith input, and yi is its label, and it is yi is a scalar. It's not a vector because it's either 0 and 1. But for binary classification, which class? And oi is a corresponding output, which is also a scalar. So you can, so this is a scalar. Xij is also a scalar. The jth element of xi. You multiply these. Also, eta is a scalar, positive scalar, and you update wj. Also, for bias, xij is 1, and you have yi minus oj. So if you set xi 0 to 1, so you add one additional dimension for bias, then you can summarize these two equations to be equation 3, right? If you set xi 0 to 1, then here j goes from 0 to d, but for the other one j goes from 1 to d, and for bias we don't have j, and I also goes from 1 to n for all of the points. Is it clear? Right? Okay, and let's interpret it. What does it mean? Consider equation 2 or 3, doesn't matter. When when output is exactly equal to yi, because we know yi is either 0 and 1, is target label. Oi is also either 0 and 1 because of this activation function. This function outputs either 0 and 1 or 1. So when yi is exactly equal to, when oi is exactly equal to yi, then this update, this is the update, becomes 0. And it doesn't update because it's already desired. But when there is difference between them, it updates the w. This is called Hebbian learning. I know it's very simple, it seems simple, but it works somehow. Okay? And as you see, it has the idea of Hebb. What did Hebb say? Is that when two neurons fire with each other, they make it them strong. So again, here it means that if OI and YI are the same, if they are the same, don't update that. Otherwise, update them. Okay, in batch training, what do I mean by batch training? Batch learning or batch training of Hebbian learning. So what was here in equation 2 or 3, we were giving the inputs one by one. So we have n data points, we give them one by one. But in batch learning, we have n data points, we divide it into several batches. Assume batch size is b. Okay, is b. Then we have n data points. Then it means that we have n over b. This is just to make it integer. Okay, it means round to below. So floor. It means floor. So this means we will have this many batches. To divide your data points into n over b batches, each of which is b of size b, right? And then for each batch, you consider this Hebbian learning all together. So you have summation of yi minus oi xij. Then you will do it for all batches, or for the first batch, for the second batch, for the third batch until the end, and also for all dimensions, right? You can also write it in the, if you add additional dimension, you can summarize equation 4 to one formula also. So again, interpretation, I think I already said that when the output OI is the same as the target label, sorry, this is YI, when we should, then we should not have any update. The update would be 0, right? Okay. Now, what we learned was perceptron with binary activation, 0 and 1. What if it is signum or sign? So signum is, it's another name for sign. Sign function or signum function. It means that the levels are -1 and 1. Okay. Then the update in the Hebbian learning will be this equation 5. Do you know why? Take a look at this. Equation 2. Wj equals Wj plus eta yi minus oi xij. So we had this, right? Correct? Then if yi and oi are the same, we shouldn't have any updates. Exactly correct here. But now let's talk about this part. When yi and oi are not the same, then what happens? We know that yi and oi is now either -1 or 1, not 0 and 1. Then it means that they become either 2 or -2. If they are both -1, then we have yi is -1, then we'll have -2 because 2 is here, -1 is here. If they are both 1, then this would be 1, and 2 is also here, would be 2, either 2 or -2. So it becomes simplified in equation 5 if we have signal or sign activation function. So rather than saying class 0 and 1, we have class -1 and 1. Also for the bias, we don't have any xij because xij is 1. If the activation function is a sign in the okay, now batch learning again. We have batch learning. Now we have summation over the batch. But now we have the indicator function, whether oi is not equal to yi. Why? Because for the ones where oi equals yi, which is desired, there is no update. The update should be 0. So we only have this update for the ones in the batch whose oi is not the same as yi. Is it clear? We also can have it for the bias. In bias, xi0 is 1. Okay, now, yeah, I think I already talked about the proof, but I have provided the proof here. When the output oi and the target label yi are either +1 or -1, so let's consider 4 cases. They're both 1, 1 -1, -1, 1, and -1, -1. If they are the same, it will be 0. If they are 1 -1, we'll have 2 eta xij, so we can have 2 eta yi xij because yi is 1. When we have this case, we'll have -2 eta xij. I can replace with this -2 by yi. The proof for Perceptron with signum activation function. There is also another proof so there are 2 proofs for equation 5. 2 proofs. This proof was simple. Okay, this proof 1 was simple. Proof 2 is a bit more complicated but insightful. Right. This credit is for Professor Botzi, and I think it's very interesting. You'll see. So you can see with signum activation function, Hebbian learning is kind of gradient descent. You'll see. So it's optimizing actually. Optimize. Let's see. We want to find a linear decision boundary. Linear decision boundary. So we have 2 classes, as I said, binary classification. We have 2 classes. Linear decision boundary, where one class falls in one side and the other class falls on the other side. Assume they are linearly separable. So you can have a line between them. We have a linear decision boundary. The equation of a line for linear decision boundary is this, right? This is the equation of a line. In d-dimensional Euclidean space, that if W and X are both d-dimensional vectors, then we'll have W transpose X and W transpose plays the role of slope here, and also have W0, which plays the role of bias or intercept, right? W0 is a scalar. However, W is a vector. So X is d-dimensional data point. W, you can see W, which plays the role of a slope, as a normal vector. This is W, which is orthogonal to the line. Okay, it's a normal. It's called normal vector, the line, linear line, and W0 is the bias or intercept of the line. Consider any 2 points, x1 and x2, on the decision boundary. Any 2 points on the decision boundary like this. See this figure. So we have x1, x2 on this line, right? X1 and x. Okay. As the line passes through each of them, they both satisfy equation 9. So whatever point we have on the line, they should satisfy the equation of the line, right? Therefore, we have this for W for x1, also have this for x2, right? So W transpose x1 plus W0 is 0. W transpose x2 plus W0 is 0. Both 0. Therefore, they are equal to each other because they are both equal to 0. So you can say W transpose x1 plus W0 equals W transpose x2 plus W0. Now, bring the W, so these two cancel each other, W0s, and bring this one to the other side. So we will have, and you will have W transpose x1 minus W transpose x2 equals 0. Now left factor out W transpose. We have W transpose x1 minus x2 equals 0. What does it mean? When inner product of two vectors is 0, it means that they are perpendicular. So W is perpendicular or on the x1 minus x2. x1 minus x2 is also a vector, right? Connecting x2 to x1. W is also a vector. So this is x1 minus x2. This is W, and as you see, they are perpendicular to each other. Okay, and by the way, W0 is the intercept here. W is the normal vector. Okay, we know that. So interesting. Now consider a point x0 on the decision boundary. Now consider a point x0 on the decision boundary, and the point x on one of the sides of the decision boundary, one of the classes, right? Such as this. So x0 is on the line, and x is on one of the sides. As x0 is on the line, again we have W transpose x0 plus W0 equals 0. Why? Because x0 is on the line, so it should satisfy the equation of the line. Then rearranging this gives us W0 equals minus W transpose x0. So far clear. Okay. Now assume the normal vector W is normalized, means that its length is 1. It has unit length. The distance of point x, see, this is the point x. The distance of point x from the decision boundary means this distance. So this distance that I'm bolding, this distance is what I denoted by D. You can see it as W transpose x minus x0. Why? Because in geometry you can see it. So consider this triangle. This is x minus x0. If you project it onto the vector W, this length will be W transpose over its L2 norm times x minus x0. So this is well known. This is the length of a projection of a vector on another vector. See it in geometry, okay? However, if W is normalized, L2 norm of W is 1. Therefore, it goes away. So you will have this. This is the distance, right? W transpose x minus x0. Now, multiply on this on the terms. So you will have W transpose x minus W transpose x0. By the way, W transpose x0 here by equation 10 was minus W0. We have minus here, we have minus here, they cancel each other, we'll have plus W0. Right? I'm putting this here. Okay, so distance became W transpose plus X plus W0, where X is this point. Okay. This distance should be non-negative. So we need to have absolute value because W transpose X plus W0 might be negative, negative quantity. But it should, distance by nature should be positive, not negative. Therefore, I need to have absolute value. However, the absolute value is not a smooth, hard to take derivative from, non-differentiable, not a smooth. Therefore, we can multiply the distance with the target label to make it always non-negative. This is an important technique in machine learning. Notice this. As far as I remember, this technique was also used in SVM, support vector machines. Take a look at it carefully. So therefore, we can, in order to get rid of the absolute value and make it smooth, but still have the behavior of absolute value, we can say, we know that the labels are +1 and -1. Y is either -1 or +1. Therefore, I can say, when that Y is +1, and assume this is a class positive. This is a class negative. +1, -1. Here is W -1, here Y is +1, here Y is -1, right? When Y is +1, I know I'm on one of the sides, on the positive side of the line. When Y is -1, I'm below the line. W transpose X plus W0 less than 0, it means that I'm below the line. Greater than 0, it means that I'm above the line. Okay. Therefore, when Y is +1, this should be positive. This is positive. When Y is negative, this is also negative. Therefore, I can multiply them to each other. So it's always positive. Why could we do that? Because Y is either -1 or 1. Now I think you see the reason why in machine learning, sometimes rather than using 0 and 1, they use -1 and 1. This is the reason. Because they want to use these kinds of tricks. Otherwise, why do we make binary 0 and 1, -1 and 1? Because of these tricks. Okay. So by multiplication of Y and W transpose X plus W0, we got rid of the absolute value, and it is smooth. Okay. So distance was this. Now, a possible cost function. Now we want to have a cost function for perceptron. It can be a number of misclassified data points to be minimized. We can minimize the number of misclassified data points. However, the number of something is discrete. It's not differentiable. It's hard to optimize. It's discrete and hard to optimize. So let's optimize the distance as the cost function. Rather than optimizing the number of misclassified data points, let's optimize the distance. That's the reason why we calculated the distance. Approach 1. So we have two approaches now. Why do I show you different approaches? Because I want you to learn different techniques. I know these are basic things we need to go through, but along these, I want you to learn the techniques in machine learning. So approach 1, we want to maximize the distance of points from the decision boundary. So minimizing the number of misclassified data points, you can see it as maximizing the distance of points from the decision boundary, right? So the more they are separated from each other, the better that decision boundary is. In other words, assume you have these points, you have this class 2. This is also decision boundary. This is also decision boundary. This is also decision boundary. Which one is the better one? This one. Because the distance of the classes from that decision boundary is a bit larger. Therefore, it has better generalization. What do I mean by generalization? In the test phase, when a point comes here, this is in class 2, in class -1. However, if we choose this point, this decision boundary, it would be determined as class star or +1. So for better generalization, we can maximize the distance. Okay, now this might ring something in your head for some of you who already know SVM. Support vector machine has the same idea. However, there is a difference. Otherwise, Perceptron would be support vector machine. There is a difference. Is that here we are considering, so we have summation, see? We are considering the distance of all points from the decision boundary. However, support vector machine considers only the distance of the closest points to the decision boundary. So only considers these points, and it calls them support vectors. Hence the name support vector machine. So only considers the closest points to the decision boundary called support vectors, and then tunes the distance based on those closest points, because those points are most candidate to be confused with each other. This is the idea behind SVM. Our perceptron here is saying that let's consider the distance of all points from the. Okay. So we use gradient ascent. Why do we use gradient ascent? Because we want to maximize. That gradient descent is for minimization. Gradient ascent is for maximization. For maximizing the distance of points from the decision boundary. Soon, in a batch, consider a batch learning. So I goes from 1 to B. Then we'll have, this is the distance, right? We found it. We found the distance in equation 13. Right? Now summation over the batch, all of the distances over in the batch from the decision boundary. Okay, this is a distance. Take derivative with respect to W. What is our parameter? W, right? Also, W0. So both W, which is a d-dimensional vector, and W0, which is a scalar. Both are learnable parameters we want to find. Okay. The derivative of distance with respect to W and W0. What is it with respect to W? By the way, why do we take derivative? Because I want to do gradient ascent. In optimization, the first thing which we should do is taking derivative, right? So take then this derivative of this with respect to W. What is it? Summation of yi xi. Right? Derivative is a linear operator. It can go through the summation. So it passes the summation. Also, we have yi w transpose xi. With respect to w is yi xi. Also here, with respect to W0, we have, again, it goes through the summation of yi W0 with respect to W0. So it will be summation of yi. We should use gradient ascent, therefore we can say this. This is plus y because it's gradient ascent. If it was gradient descent, it would be minus. Then this is the learning rate. We have this. Also for W0, we have this. We do this for all j from 1 to d. This means for all, right? Okay. What is it? We just proved Hebbian learning of perceptron with a signal activation function. Recall equation 5. Just proved that by gradient S. So you can see Hebbian learning, although it seems very simple, is kind of gradient ascent, maximizing the distance. Interesting. Sometimes you don't see the interesting thing behind the algorithms. Very interesting. Now, approach 2. That was approach 1 that we went. Approach 2. We take the distances of misclassified data points as a cost function. So approach 1, we said let's maximize the distance of points of classes from the decision boundary. Approach 2, now consider the misclassified data points. Okay. And the distances of misclassified data points as a cost function. Of course, we want, so see, according to equation 12, the distance in equation 13. What was equation 12? Do you remember this equation 12? Also equation 13. So D was Y times Y transpose X plus W0, right? Now, the distance in equation 13 is for correctly classified elements. Do you agree? Guys, do you agree? So Yi times W transpose Xi plus W0 was for correctly classified points. As discussed in equation 12, I said if it's on above the line, y is plus 1, W transpose X is plus W0 is greater than 0. If it's below the line, y is minus 1, W transpose X plus W0 is less than 0. This is for correctly classified. For misclassified, it's the other way around. Therefore, we will have minus here. Minus here. So yi. So this is for correctly classified. Minus of it is for misclassified ones. Right? Again, as labels are minus 1, 1. So we should multiply distance by minus 1 to have the distance of misclassified points. And the derivatives are these. We'll have minus here again. Now let's use gradient descent. Why? Because we want to minimize the error. What is this? This is the error now. The distance of misclassified points. We want to minimize that, right? For example, these are the classes. By the way, this is misclassified. This is the distance. I need to minimize it to bring it here. Minimize this. So I use gradient descent. Now I have minus because of gradient descent, also minus in the derivatives. They cancel with each other. We'll have positive. Okay. Again, it proves the Hebbian learning of perceptron with signum activation function. Which we had. Okay. Now problems with perceptron. Perceptron is for binary classification. So it's for that can't be used for multiple classes, although we can consider we can see multiple classification with multiple classes as by pair of classes. Like for example, with 3 classes, class 1 and 2, class 1 and 3, class 2 and 3. Although, but still it's binary classification. In 1969, the biggest problem with perceptron is this. In 1961, 2 people, Minsky and Oppert, published a book titled Perceptrons and showed that perceptron can only solve linearly separable problems. Apparently before that, they were not aware of that. They hadn't thought of it. In their book, they said, okay, assume the classes are like XOR. What do I mean? This is the first class. This is the second class. Some of the points in the second class are here and some are here. Some of the points in one of the classes is here and some of them are here. Now separate them. Of course, these are non-linearly separable. They show that you can't separate them using perceptron. Perceptron can't solve this problem. For example, they showed that cannot classify XOR using perceptron. And because of this, the interest in perceptron dropped. Suddenly they thought, oh, apparently we haven't solved AI yet. Okay. Do you remember I said they were very excited? They thought that they had solved AI. Therefore, researchers lost interest in perceptron and artificial neural networks. Researchers guessed that they should have multi-layer perceptrons. So now they wanted to save perceptrons and say, what can we do to perceptron in order to handle non-linearly separable classes? They said, okay, maybe we should stack them up. Maybe we should have several of them stacked. So they said, let's have multi-layer perceptron. Perceptron is just one. Let's have several of them. But they did not know how to train multi-layer perceptrons. They didn't know that. Okay. Also, perceptron cannot generalize well enough. It can't. Why? Because consider these 2 classes. Perceptron, if we train perceptron, so because consider that Hebbian learning, in Hebbian learning, gradient or gradient descent approach that we went, you need to start with some random solutions, right? So you should to have some random W and W0 and then update it until convergence. Whatever random, based on random solution, you might end up with any of these lines. Consider they are linearly separable, so perceptron can handle it. However, you don't know which one you will end up with based on your initial random solution. It finds one of many possible decision boundaries. And that was one of the hints for the developers of SVM. They said, let's find the best one. Support vector machine finds the best one. But Perceptron was finding one of them. And as you see, if, for example, this line is found by Perceptron, it might not generalize well, because one test point might come here, which is supposed to be in class dot, but it is identified to be class cross by Perceptron. So it doesn't generalize well. Yeah. Because of, by chance, maybe one of the good points, by chance, maybe one of the good points would be found. One of the good decision boundaries would be found, but not necessarily. As we can't go in the algorithm, we can't go with chance. We need to be good all the time. So because of this problem, two things were developed. ADALINE, which generalizes better. ADALINE generalizes better. And also support vector machine, or SVM, which found the best decision boundary by optimization of the distances of the support vectors from the decision boundary. If you run SVM on this problem, it will give you this line, which has the largest distance from the support vectors, which are these. So it generalizes very well. However, Perceptron can find one of these. So ADALINE and SVM, they try to make it better. So let's talk about ADALINE. This is the history of neural networks from previous century, which we are coming on. Okay, ADALINE. In 1960, Woodrow and his student Huff at Stanford University. As you see, although these algorithms are very simple, but they were developed in very high-tech universities such as Cornell, Perceptron, or Stanford, ADALINE, right? So Woodrow and Huff at Stanford University proposed a method named ADALINE for adjusting weights. In 1960, articles claimed that robots can think. So every time they developed something, they were very excited. They thought they have solved AI. Again, they thought that articles were saying that, newspapers and these things, that robots can think now. So it has more generalization compared to Perceptron. ADALINE, what does it do? It minimizes least mean squares error. What do I mean by least mean squares error? Least means minimization. So you minimize mean squares error. What is mean squares error? Just example, you have yi minus oi. So this is error. This is a square. You have several of them. I maybe on a batch something, okay, and maybe you can take the mean. So this is mean. The mean squared error is this. So mean of error, which is a square, and then you minimize it. This comes from minimization, right? Okay. So least mean squared error, or LMS error, using gradient descent. So in order to minimize it by gradient descent, you have this take derivative and gradient descent, you know that, yes? The parameter is parameter minus eta, the gradient, right? Where eta is the learning rate. Okay, the training method is referred to as LMS algorithm, short for least mean squares error, or Woodrow-Huff learning rule. we draw half learning. Okay. This is ADALINE. Very similar to Perceptron. You see that? Very similar. What is the difference? Can anyone tell me? What is the difference of this Perceptron? So Perceptron, what?
Not linear,
Linear, which one?
not linear, like it is like squared.
Yes, but I'm saying about the structure. The different, I agree, the loss is different. So one difference is loss, you're right. There's another difference in the structure. So in Perceptron, the feedbacks comes from the output of the activation function. But in ADALINE, it comes from before activation function. In other words, we are comparing the target label with the float number. So because this here, after activation function, is either 0 and 1. But before activation function, it might be half, it might be 0.7, whatever. It might be 3, it might be minus 1.2. So it is a float number before the activation function, and you compare it. That's why it generalizes better. So it doesn't compare the target with the crisp output, compared with the float output before the activation. The target label is compared with the output before activation function. This is why Perceptron compares the target label with the output after activation function. And this is LMS error. Okay, let's take a look at it. So what is this? This is exactly the summation here. Summation W1x1 until WDXD. We have W0x0, which is 1, which is W02. And then, as you see, we don't pass it through F. There is no F here. There is no F here. Okay? Then we have yi minus this. Then squared. Then this a scaled mean doesn't matter. This is in optimization. This scale is not much important. Okay? A scaled number, and this is least squares error. Okay, where B is the backside. This is X and yi is its target label, right? Okay, now let's optimize it, the gradients. So what is it? So this is the error. Let's take the gradients, the derivatives. Derivative of error with respect to Wj. What is it? So derivative is a linear operator, can pass through the summation. And by the way, why do I have 1/2 here? What's the philosophy? I want to cancel 2 in the derivative because this is a square. X squared, its derivative is 2x. I want to cancel that 2. Okay. Then, so derivative of this squared. So by chain rule, we will have this. And also derivative of this with respect to Wj. What is it? With respect to Wj is xij. Right? One of you might wonder, where did summation go here? See, this summation comes from here. Understand? No, let's not talk about that. I think it will confuse you. Doesn't matter. I think you got my idea. So again, this is chain rule. So this is a squared. Again, this squared is 2 of this derivative. 2 cancels with this 1/2. Then derivative of this with respect to Wj is xij. Okay. We do it for all j from 1 to d. Okay. And also derivative of this e with respect to W0. With the same explanation, we have this, but we don't have xij anymore. Because there is no xij here. Right? Clear? So we have these 2 gradients or derivative. Now I do gradient descent. Wj is Wj minus eta. Eta is the learning rate, positive number. Derivative of e with respect to Wj, also W0 minus eta, derivative of e with respect to W0. And we do it for all j from 1 to d, right? So this is, as you see, ADALINE. Why is it at that time it was hard to do this? Because at that time they were although gradient descent is very old, but usage of gradient descent in science was new. Gradient descent is very old, but usage was new, especially in AI. Okay. Now ADALINE. ADALINE. Okay. Yeah. Now ADALINE. So ADALINE at Stanford University, Woodrow and he's a student again. He's a student stacked. So the main professor who was working on ADALINE and ADALINE was Woodrow at Stanford, and his students, they stacked several ADALINE neurons to be able to have nonlinear classification. Okay, so ADALINE was for linear classification, linearly separable. But again, this was the mindset of all researchers in AI at that time, around that time, saying that in order to be able to do nonlinear classification, to separate nonlinear classes, we need to stack several linear classifiers. So ADALINE or Perceptron, these are linear classifiers. Maybe by stacking them and maybe finding a way to train the whole thing, the whole system, it will be able to classify nonlinear classes. So this was the mindset behind all of them. So they proposed several things in different times. So in 1962, they proposed ADALINE Rule 1. So by the way, ADALINE stands for many ADALINEs, or multiple ADALINEs, doesn't matter. Okay. So ADALINE Rule 1, MR1, brief one. Okay, MR1 in 1962 was proposed, but they could not adapt the weights of the hidden output layer. By the way, this is ADALINE. This figure, I think, take a look at it. So we have x1 to xd as input. The neurons here, each of which is ADALINE. Remember we talked about ADALINE? Each neuron is not a perceptron neuron. It's ADALINE neuron. Maybe the reason is that they were competitors. ADALINE and ADALINE, they were from Stanford. Perceptron was from Cornell. They didn't want to put Perceptron in their network. Okay, so their neurons were ADALINEs. Although at the end, Perceptron won the game. Nowadays, we have multi-layer perceptrons in our network. Okay, but we have ADALINE neurons, and as you see, we can stack them together. So we have maybe multiple layers of ADALINEs, or many ADALINEs, or ADALINE. So they had developed several rules. We don't go through the rules, but the history is like this. 1962, they could not adapt the weights of the hidden output layer. So this is the hidden output layer, right? ADALINE Rule 2, MR2, they proposed it in 1988. You can see so many years they were working on this. And improved MR1, ADALINE Rule 1, to be able to also train the weights of the hidden output layer. So at ADALINE Rule 1 only was training this layer. ADALINE Rule 2 was able to train both layers. ADALINE Rule 3 proposed in 1990 and changed signal activation function. Do you remember in ADALINE we had signal? Take a look at that again. Recall. What did we have in ADALINE? We have signal. Sign, right? 0 and 1. No, sorry. I think. Yes, sorry. It can be either 0 and 1 or minus and 1. Doesn't matter. But they changed it. They changed it to what? Sigmoid. And what is sigmoid? Sigmoid is like this. Rather than be binary sharp, let's make it smooth. Make it smooth. So the output would not be only 0 and 1 or minus 1 and 1, doesn't matter. It would be a float number in the range, 0 and 1, right? So they improved that. As you see, at that time, around, what was the time? At that time, around 1962 and 1988, people were thinking about logical gates. Whenever they wanted to do AI, they thought, okay, computers are based on logic, so only 0 and 1 or minus 1 and 1. However, later they thought, why not make it float. Why not make it float? Maybe they were also inspired by fuzzy logic proposed by Lutfi Alizadeh, professor in Berkeley. Okay. Fuzzy logic says what? It was a war against binary logic. Rather than saying that 0 and 1, let's say 0.7. How am I feeling now? I'm neither good nor bad. I'm 0.7 good. Okay, so something like that. So that was fuzzy logic. At that time, it opened eyes. Maybe we shouldn't only be binary. We can be a float number. Okay. So again, in 1990, they changed the signum to sigmoid function for having float outputs rather than purely binary outputs. Okay, let's have a break and come back at 8:30. Okay. Thank you.
सब्जी तो पानी में बनाता हूँ और उनका डिफरेंस है क्या पानी में बनाती हूँ
Okay, now we talk about. Okay, guys. Now we talk about logistic regression. Guys, please. Now we talk about logistic regression. Its name might be a bit misleading. Logistic regression is used for classification, not for regression. Okay. Why is it called logistic regression? Because it outputs the probability of belonging to one class, one of the classes, and this probability is a number, a float number between 0 and 1. So you can see that the score of, or the probability of belonging to a class, it outputs that, it regresses that, it predicts that probability, but using a threshold, we found on that probability, we found out which class it belongs to. The logistic regression is used for classification, although it regresses or predicts the probability of belonging to a class. Okay. And why is it explained in this course? How is it related? Because we will see that logistic regression can be seen as a neural network with one neuron. One neuron. Okay. So again, this is in this slide. In this slide deck, is about training one neuron, right? Okay. So it is popular. Logistic regression is popular in biostatistics and bioinformatics. Usually, in these areas, if you write a paper using logistic regression, it gets accepted. This at that some time ago. Okay. Also, consider X to be a d-dimensional vector. And Y, the class label, which is a scalar. Okay. Now, Bayes rule. So Bayes rule. This is Bayes rule. Probability of Y given X equals the probability of X given Y times P of Y over P of X. Why? Why is it true? Because we can write joint probability of X and Y as probability of X given Y, P of Y. We can also write it as probability of Y given X, P of X. When I say given, it means a conditional probability. Okay. So you set them together, set them equal to each because they're both equal to P of X and Y, joint probability. And then if you rearrange that, we will get the Bayes rule. Okay. So, and these two, P of X and P of Y, are called prior on Y and prior on X, P of Y, P of X. This is usually called likelihood. This is usually called posterior. Okay. And P of Y given X is the posterior and P of X given Y is the likelihood. Do you know the reason of these names? So P of X given Y. means that given the label, how likely is to use for you to see that data? X. Likelihood. And posterior, I think it's because you can see given the data, what is the label? And usually label comes after the data. So you can see it as a post thing. Compared to prior, we have prior thing, post thing, and how likely it is. So these are the philosophy behind this name. In contrast to linear discriminant analysis, I will go through LDA in the other course, statistical machine learning. Okay, but basically, what does it do? What does LDA do? Just briefly mentioning. LDA is for binary classification. Consider two classes linearly separate. Okay, LDA maps fits. LDA fits some Gaussian distribution on each of the classes, like this, also this. Okay. So it tries to learn the mean and the covariance of these distributions. And then where they intersect, these two Gaussians intersect, that will be the boundary. For example, in 1D, if I want to draw it, 1D, consider this is one of the classes and this is another class. I fit a Gaussian. Also, I fit a Gaussian to this. Where do they intersect? Here. This is the boundary. LDA does that, linear discriminant analysis. So it tries to learn the best mean and covariance for each of these classes. Okay? Covariance and mean. So in contrast to LDA, logistic regression works on the posterior rather than working on likelihood. So LDA works on likelihood. So as I said, given y, which class it is, it fits a Gaussian distribution on that class. So P of X given y is important in LDA. So it works on the likelihood. However, logistic regression says, why do I work on the likelihood? Let me work on the posterior. Because usually you work on the likelihood, you also have the prior, you reconstruct the posterior. Let me work directly on the posterior. This is what logistic regression says. So it works on P of y given X. Given data, what is the probability of that label? So you give me some data, I tell you whether it's in the class 1 or 2. This is posterior. Likelihood says, in this class, what is the probability that I have this point? Logistic regression is a binary classifier where it assigns probability between 0 and 1 for belonging to one of the classes. So when you give me the probability of belonging to one of the classes, 1 minus that will be the probability of belonging to other class. So the summation of probabilities should be 1. It's either in this class or in the other class. So I can only consider this as one probability because the other probability is 1 minus that, right? The logistic function, logistic regression uses a function named logistic function, also called sigmoid function. We'll see that. So the logistic function used in logistic regression was initially proposed in 1845. This is so much old. 1845 for modeling the population growth. Why? Because as we will see, logistic regression is something like this. 0 and 1. And it can model the population growth. Usually, initially, it grows very fast and then it almost stagnates. Because you can't always increase the population. You will have lack of food and lack of hygiene and all of these things. So some people die. Therefore, it will go up, but suddenly it stagnates. That's the reason. It was further improved in the 20th century. You can see these references. They also this reference 13 for the history of logistic regression. So it considers the classification problem as a regression problem. Again, classification problem, it sees that as a regression problem, where it regresses or predicts the probability of belonging to a class. Okay. It first considers a linear regression. So see, as I said, it's doing regression, but by threshold, it finds out which class it is. So its idea is this, it's built up in this way. It says, let me do linear regression, the simplest regression. So let me fit a line to data, okay? Linear regression, what is the equation for a line? Beta transpose X plus beta 0, right? By the way, this beta 0 is a scalar, beta and X are vectors, right? Okay. However, in order not to have the bias, it assumes that X is D plus 1 dimensional. An idea that we also had in Perceptron and these things. So let's add a fake dimensionality and set that to 1 or bias or intercept. Okay, so X will be X1, XD, and at the end 1. So in Perceptron, we added 1 in first of the vector. Here we are adding it at the end, doesn't matter, okay? Then beta will be also D plus 1 dimensional, is a learnable parameter. So by the way, by doing this, beta transpose X plus beta 0 will become only beta transpose X, right? Okay. And beta is the learnable parameter, X is the data. As a result, the linear regression becomes beta transpose X. However, there is a problem here, because I want to output or predict some score or probability, and the probability needs to be between 0 and 1. Beta transpose X can be between minus infinity to infinity. So I need to make it between 0 and 1. How do I make it? One way is doing logistic regression. Logistic function. Logistic function or sigmoid function, what does it do? It takes anything between minus infinity to infinity and maps it to between 0 and 1. It's a function or map from minus infinity to infinity to range 0 and 1, right? Okay, so by the way, there are several ways to make, several techniques in machine learning to make something behave like probability. Let me tell you. One of them is logistic function, sigmoid function. You have something, you bound it, you want to make it behave like probability. One of them is logistic function. Another thing is that assume you have now a bunch of data, a bunch of scalars. You want them to become like a probability distribution. A technique is that you replace every point with that point over summation of all of the points, and they will sum to 1. Right? So these are the techniques. Technique 1 for one scalar, technique 1 is using a logistic function. Technique 2, if you have a bunch of scalars, we want them to behave like probability. We divide each of them by the summation of all of them. Then they will become between 0 and 1, each of them. And they will also sum to 1. Right? Technique 3 is using softmax. Softmax is like this, e to the x. No, I think it was, yes. Summation of e to the x. So again, it's similar to the technique 2. Technique 2, what did it do? Technique 2 was xi over summation of xi. Softmax is e to the power of xi over summation of e to the power of xi. Okay, you see the difference. This is technique 3. This is called softmax. What is its interpretation? Of course, they will sum to 1. They will be between 0 and 1. But what's the difference between technique 2 and technique 3? Technique 3 has some advantage. It makes it like a Gaussian distribution. You know why? Have you seen the Gaussian distribution? PDF is e to the minus mu was sigma squared. There's some scalar to normalization factor. Okay. So e to the something becomes like, by the way, e to the minus x side. E to the x side doesn't matter. E to the minus x side, I think is correct. So in this way, e to the minus x side is like a Gaussian distribution. However, it doesn't sum to 1. It doesn't integrate to 1. In order to make it sum to 1 or integrate to 1, you need to some normalization factor. Normalization factor of Gaussian distribution might be hard to compute. Let's make it easy for us and just sum each of them, divide each of them by the summation of all of them. Did you get it? Okay, so 3 techniques I told you in machine learning for making data behave like probability. The first technique was for one scalar. The technique 2 and technique 3 were for a bunch of scalars. Now logistic regression is using the technique 1. Because beta transpose x is a scalar, right? So it uses logistic function or sigmoid function to make this regression between 0 and 1. This is the logistic function. So assume we have 2 classes, y is either 0 or 1. Then logistic regression models the posterior, as I said, work on posterior. Posterior using a logistic function, also called sigmoid function. So we have either y is either 0 and 1. Therefore, one posterior is p of y equals 1 given x. The other one is p of y equals 0 given x. Okay. P of y equals 1 given x is this e to the.
How would that come from e to the power beta t?
What?
So the sigmoid function is 1/1 plus e to the power minus.
This is sigmoid. This is sigma.
Yeah.
Okay.
So if you will consider for y is equal to 1, it should be the one which is for y is equal to 0.
Sorry, what? Can you repeat?
The function e to the power beta transpose of x was 1/1 plus e to the power beta transpose of
You
x.
mean this, right?
Yeah. How did that came?
I'm saying that it's related to logistic regression. So to logistic function. Let me explain this way.
Yeah.
Take a look at sigmoid function is 1 over
Yeah.
1 plus e to the minus x. This is called sigmoid function or logistic function. Okay. Let me explain step by step. So why is it behaving like this plot? Why is it this plot? Bring x to minus infinity. So by the way, let x be 0. Then this will be 1. Then we'll have 1 over 2. It's half. Let x go to infinity. Then what happens? This goes to 0. E to the minus infinity goes to 0. Then we'll have 1. Let x go to minus infinity. Then we'll have the denominator will blow up because we'll have e to the infinity. So it will become 0. So now this is sigmoid function. Similar to the sigmoid function, if you set x to be minus beta transpose x, let's set x to the minus beta transpose x in the sigmoid function. We'll have 1 over 1 plus e to the beta transpose x, right? Minus beta transpose x is minus, cancel the minus in the logistic function. We will have this. We will have this plot. Let's analyze this plot. Beta transpose x, if it goes to infinity, denominator blows up, it goes to 0. If it goes to minus infinity, denominator becomes 1. So 1 over 1 is 1. If it's 0, beta transpose x is 0. This axis is beta transpose x, right? If beta transpose x is 0, then we'll have 1 over 2. Correct. Okay, so that's the reason. As you see here, I have used in equation 22, I have used sigmoid function where I have replaced its variable with minus beta x, beta transpose x, right? Is it clear? Okay, now we have another thing too. E to the beta transpose x over 1 plus e to the beta transpose x. Let's see its behavior in the plot. Let beta transpose x go to minus infinity. Numerator will be 0, denominator will be 1. Goes to 0, this will go to 0 too. So we'll have 0 over 1, which is 0. Then here, let beta transpose x go to infinity. The numerator will blow up. The denominator, I think, will blow up too, but it is indeterminate. But if you solve it, take limits, it will go to 1. Okay. And let beta transpose x be 0. So we'll have e to the 0, which is 1 over 2. Okay, this is correct. So this is behavior. Now we have these two functions in logistic regression. Let one of them be p of y equals 1 given x, and the other one be p of y equals 0 given x. And why? Because we know that they should sum to 1. So p of y equals 0 given x is 1 minus p of y equals 1 given x. If you put this here, 1 minus this formula becomes this. So 1 minus equation 21 becomes equation 22. Okay. Beta is a learnable parameter. X is a data. Beta transpose x, you can see it as a variable in the sigmoid function. Minus beta transpose. Is it clear now? Okay. No? Well, which is not clear? Which one?
Could you please look at why it becomes the sigmoid function?
Oh, okay. This is definition of sigmoid function. This is definition of sigmoid function. Okay. If I set x rather than x, I use minus beta transpose x. Do you agree that I will have this? Yeah. I use it as I choose to use p of y given 0, x y equals 0 given x. Okay. Then 1 minus this, 1 minus equation 22 becomes 21. Equation 21. Why? Let's prove it. 1 minus this becomes 1. Give me a second. These two cancel each other. I'm making any mistake.
Yeah, it should be 1 plus e raised to beta transpose.
What?
There should be the plus.
Which
If you're
one?
going for the sigmoid, it is 1 upon 1 plus e to the power minus x. So if you are
This is my. Which one is minus?
the sigmoid function on the bottom,
Okay.
is 1 upon 1 plus e to the power minus x. So if you are taking it to 0, the p of y is equal to 1 should be of p of y is equal to 0. So you have substituted the terms. As far as I know.
Can you repeat?
Yeah. Can you come?
That's fine. That's fine.
Okay. I can explain you. Right?
Yeah, sure.
The thing is, the sigmoid function is 1 upon 1 plus e to the power minus x. We have two samples, sample 1 and sample 0. So for sample 1, if we'll consider sigmoid as 1 upon 1 plus e to the power minus x. So for sample 0, it should be 1 minus 1 upon 1 plus e to the power minus x. So the terms of y is equal to 1 should be of the term p of y is equal to 0 with a minus sign.
I believe this is exactly what you said, but rather than minus 6, I'm having
Because there is a sign difference. That is what I asked you in the starting. There is a sign difference.
So let me see. Guys, see what I'm doing. 1 minus. Now I'm putting equation 21 here. E to the beta transpose x over 1 plus e to the beta transpose x. What do I have?
Plus e to the beta transpose.
This in the denominator. What do I have in the numerator? 1. So that's correct.
Yeah, but you are using the different equation. I'm using the sigmoid basic equation.
I know, but I'm saying that in the sigmoid, I can put whatever I want in X. Let me put minus beta transpose X. Right? I can put Benjamin 1/1 plus e to the minus Benjamin. Right? Rather than Benjamin, I put minus beta transpose. Did you get it? Did you? I think you got more confused. Okay, let me. So, let's recap.
Yes, yes.
Guys, let's recap. Guys, please, guys. So, in the sigmoid, there is some function named sigmoid function. Its definition is 1/1 plus e to the minus t. This x is a variable. I can put anything in it. Let me put minus beta transpose x in it. I will get equation 22. I will also define equation 21 as this. And interestingly, they sum to 1. These two, if you sum them, then we want. And I want that because the point is either in class 0 or class 1. Did you get it? I think and these are the behaviors by plots. I'm showing the and now take a look at it. Whenever, so these two plots, the second plot and the third plot, one of them is for one of the classes, the other one is for the other class. So if it's class 1, it's plot 2. If it's class 0, it's plot 3. Okay, as you see, when class probability of class 1 goes to 1, probability of the other class goes to 0. When the probability of class 1 goes to 0, probability of class 0 goes to 1. Correct? Okay. So now logistic regression, but interestingly, can be seen as a neural network with one neuron. Are you listening? So logistic regression can be seen as a neural network with one neuron where the activation function is a non-linear sigmoid or logistic function. This is exactly logistic regression. Why? Beta transpose X, you can see it as a neuron where the weights are beta 1 to beta d. We can have beta 0 too, because as I said, d plus 1, we have one additional dimension for the bias, right? And then you pass it through sigmoid function or logistic function. Logistic regression. Okay, but now how do we train this neuron? Logistic regression uses Newton's method in optimization. What is Newton's method? It uses both first order and second order derivative for optimization, both gradient and Hessian. Let's take a look at that. Okay, consider n data points. Consider n data points. I goes from 1 to n in data set, assuming that they are independent and identically distributed, IID. What do I mean? They're independent, they're not dependent on each other, they're random variables. They're also, their distribution is the same. If one of them is Gaussian, the other one is Gaussian, the other one is Gaussian. What? They have the same distribution. So identically distributed. This is, in short, they say it's called IID. Then the posterior over all data points is this. P of y given x. I can write it as multiplication of all, probability of all of the points, posterior of the points. Okay, the point is either in class 0 or class 1. I'm using indicator function here. Indicator function is 1 if its condition is satisfied, otherwise it's 0. So if it is in class 1, we have this term is 0. Because this will be 0, right? So then we'll have probability of y is equals 1 given x. The other way around. If the point is in class 0, we'll have second term. First term will be 0, go away. We'll have second term, and we'll have probability of y equals 0 given x, right? Why am I allowed to multiply the probabilities? Because they're IID, they're independent. Okay. as the labels are either 0 or 1, so yi is either 0 or 1. This equation can be restated as this. Good technique in machine learning again here. I've seen a lot of techniques. One of them is this. I can put labels yi and 1 minus yi as a power. I know yi is here. Here is either 0 and 1. Now, in that scenario, yi equals minus 1 or 1 was useful. In this scenario, yi equals 0 or 1 useful. Okay. So when yi is 0, what happens? When yi is 0, this power becomes 1, this power becomes 0. Everything to the 0 except 0 is 1. So this term will be 1, goes away in multiplication. I will have this correct because I want probability of y equals 0 given x. Right? Now consider yi to be 1. This power will be 0. This term will go away in multiplication. I will have the first term. A good technique. Right? Okay, now, so I replaced equation 23 with equation 24. I don't use indicator function anymore. I use the technique of powers. Now substituting equation 21 and equation 22. I mean the definition of probabilities by logistic function. In this equation 24. So this was, what was it? This probability of y equals 0 given x was this, right? So far clear. Ask me if you didn't understand. Okay. Now, equation 25 is the posterior, joint posterior. Now, we use log posterior. Usually, it's easier to optimize the log of the probability. Either log likelihood, log posterior. We take logarithm. Why is it easier? I tell you. That's also a technique in probability. Because when you assume it's IID, you have multiplication of probability, right? But when you take log of multiplication becomes summation of logs. Log of Benjamin times Jack is log of Benjamin and Jack. I mean like this. Log of Ben and Jack is log of Ben, thus log of Jack. There is times here. Okay, that's important. So I have log. This is the posterior, joint posterior. Right? Now I have sum, so log goes inside the sum. Log goes inside the sum. We have log of the terms. Okay. Now you see we are getting rid of the power because log of Benjamin to the Jack, to the power of Jack becomes Jack times log of Ben. Right? So this power comes here. This power comes here. No, here. What is this term? Also, I'm using another property of logarithm. Logarithm of A over B is logarithm of A minus logarithm of B. Because I have numerator and denominator. Okay? So far clear. Now, by the way, I had E, exponential. It cancels with log. They are all opposite operators, right? Now you can see, so there are several reasons why log posterior or log likelihood is easier to work with rather than the likelihood and posterior. One reason is that log of multiplication becomes sum of log. Working with sum is easier. Another reason is that most of the probability distributions are in the exponential family. Many of them have exponential operator in them. Many of the probability distributions. Then we'll end up with log of exponential, they cancel with each other. Okay, therefore, we'll have this yi is here and this is in the power of exponential, so it comes here. We have this, we have this, we can't simplify this second term, that's fine. Then we also, let's multiply these terms to this. So we'll have minus log of this term, also plus yi log of this term. Interestingly, these two cancel each other, right? Then we'll end up with this. So you can see we had a huge term expression for log for posterior. Then log of posterior became very simple. So we found this. Let's call it log of posterior. I think log posterior is better. Log posterior is this. Now Newton's method can be used to find the optimum beta. So our parameter, learnable parameter is what? Beta, right? Beta. Now let's find that. First derivative. As we are using Newton's method, we need both first derivative and second derivative. First derivative or gradient. What is it? Derivative of log posterior with respect to beta. Derivative is a linear operator. It can go through the summation. We have summation here. Here we have beta transpose x, therefore we'll have x only. Okay. Here, derivative of log of a with respect to a. What is it? 1 over a. And if a, we have g of a, we have chain rule. 1 over g of a, derivative of g of a with respect to a. This is chain rule, right? Therefore, I will have this 1 over this. Also, derivative of this with respect to beta. What is it? What is derivative of 1 plus e to the beta transpose xi with respect to beta? This is constant, goes 0, becomes 0. Derivative of e to the beta transpose xi with respect to beta is xi e to the beta transpose xi, right? This is here. Two chain rules, two nested chain rules are used for the whole thing. One in the logarithm, one in the exponential operator. Okay. Now I can write it, I can factor out, right factor out xi. As it is a vector, it's important whether you left factor out or right factor. Right factor out xi. Okay. So we'll have this. Any questions so far? Please don't be shy, ask. Any question? No? Okay. So now I need, guys, please listen. I need its transpose. You will see why. I need its transpose. Therefore, I transpose equation 26. So with derivative of log posterior with respect to beta transpose rather than beta. So xi becomes transpose. The whole thing here is a scalar. Transpose doesn't do anything on it. Xi transpose. Now it's second derivative. The first order derivative gradient is calculated. Second order derivative or Hessian. It's this. You can write it as partial squared log posterior with respect to beta transpose. You can't say with respect to beta transpose beta. Why? Because beta transpose beta is a scalar. Beta transpose is a matrix. Beta is a column vector. We know Hessian is a matrix. Numerator, what we are taking derivative of, is a scalar. If you say beta transpose beta, it would be derivative of a scalar with respect to another scalar, would be a scalar. to be the derivative of a scalar with respect to a matrix to become a matrix. Okay? So you can write it as derivative of with respect to beta inside derivative of the first derivative, but transpose. Okay? We calculated this. We calculated this in the previous slide. Okay. Now let's take derivative with respect to beta. Interesting. Derivative is a linear operator, goes through the summation. This term is a constant with respect to beta. Its derivative becomes 0. Now this term, this can come out. We'll have derivative of this with respect to beta, right? So far clear. Why could this come out? Because it's constant with respect to beta. Okay, now I want to calculate this. Let's see how we should calculate it. I define, this is my definition. I define e to the beta transpose xi over 1 plus e to the beta transpose xi as probability of xi given beta. You give me beta, what is the probability of xi given beta? I define it. I just rename it with this, okay? This is what I define. Therefore, I can say I need derivative of p of xi given beta with respect to beta. Clear? Let's calculate it. Let's calculate this derivative. So I'm replacing it here, what I define. Derivative of what should I say? A over b, a fraction. What was that? With respect to something, doesn't matter. It's derivative of first times b minus derivative of what is the derivative of the formula for derivative of fraction? You remember? Derivative of first times the second minus this derivative of this the first times the derivative of second over second squared. The b squared. Okay. Correct. This is the formula for fraction, derivative of fraction. You remember? I'm gonna use it here. I'm going to use it here, and note that both numerator and denominator are scalar. They're both a scalar. Although we have inner product in them, but the whole thing is a scalar. Okay? So denominator squared, I have it. Now, the first derivative of numerator is this, e to the beta transpose xi times xi. Right? Derivative of e to the beta transpose xi with respect to beta is xi. And also times the e to the thing. Also, this is the denominator because of the formula. Minus the numerator times derivative of denominator. Derivative of denominator also, 1 is a constant, goes away. E to the beta transpose xi, its derivative is e to the beta transpose xi times xi. Clear? Okay. Now let's factor out e to the beta transpose xi. Left factor out. Factor out. It's a scalar, doesn't matter. I'm factoring out it here. Okay. Also, this is the denominator. I'm not touching it. I'm left with this. Also, I'm right factor out in xi. Clear? Interestingly, these two cancel out. It's simplified to this. Right? Then I can write this squared as multiplication of two terms. Right? This, I just defined that in the previous slide as P of xi given beta. This interestingly is 1 minus p of xi given beta. You say no, calculate 1 minus this gives you this. Okay. You have also xi here. Okay. You can see we calculated this derivative and it became very simple. Substituting it in equation 28. Equation 28 is this. Right? The Hessian. Let's put it back. So I calculated this in the next slide. I'm going to put it back. So I will have this equation 29. This is the Hessian. By the way, in the exam, I don't ask you for these kinds of proofs. This is just for you to understand. Now, listen to me, please. So now we calculated derivative, first order derivative gradient, second order derivative Hessian. Okay. We can write the Newton's method in matrix form. So we calculated them for what? Element wise. Xi, C. We have Xi here. In the gradient also have Xi. Let's make it in a matrix form. It's easier to work with in matrices in computer. So I can stack them. So each of Xi's, X1, X2 is a column vector. D-dimensional column vector, I put 1 at the end for the sake of bias. So it will be D plus 1 rows. I have n points, within n of them. I have n columns. So I name it matrix X because it has all over the Xi's in it. Okay, including the bias. So it will be a matrix D plus 1 times n. Okay. Now, also I define a matrix W, which is a diagonal matrix whose elements, ith element, whose ith element is P of Xi given beta times 1 over P of Xi given beta. Why? Because I want to write this the matrix form. Okay. In equation 29, I want this term to write it in the matrix format. Therefore, I define a diagonal matrix W. It's n by n. Why? Because we have n Xi's, x1 to xn. Okay. Y is a vector y1 to yn. Because what? I have n points, so I have n labels, target labels for the class. Y is an n dimension. E, I define it as this. So each element, ith element is e to the beta transpose xi over 1 plus e to the beta transpose xi. I have this term in the gradient and Hessian. I wanted to make it matrix form. Therefore, I define this vector. E is also n dimensional. Okay, and you will see how they become this format. So let's go back to what we had for the derivative. Okay, what was derivative? I'm writing it down again here for you to know. A derivative, we found it to be this. Guys, it was this, yi minus e to the beta transpose xi, equation 26, I'm saying, over 1 plus e to the beta transpose xi times xi. Why can we write this in this format? Let's see. So here, do you agree this is the elements of P? This is the elements of P, right? No? Don't agree? What is this? Each element of P. So I have minus P here. This minus comes here. What is this yi? Elements of y. A vector y here. Right? Here xi's elements of x. So I have this here. You might be wondering why x came left. Because of the compatibility of dimensionalities. Let's see. P is n by 1. Y is n by 1. X is d plus 1 by n. We can't put x into the right side. So d plus 1 times n. The whole thing becomes d plus 1 dimensional. Correct. Why? Because our variable beta is d plus 1 dimensional. So its gradient also needs to be d plus 1 dimensional. Its Hessian should be d plus 1 times d plus 1. Hessian should be like this. So let's see. What was Hessian? Let me write it down. Hessian, we just found it here. Equation 29. Can you see? Equation 29. This is exactly what we defined as W, diagonal matrix. Therefore, I have W here. Right? Here, interestingly, we have xi transpose. So it's quadratic with respect to x. Therefore, I have x and x transpose here. What? The reason of order of matrices is the compatibility of dimensionalities in multiplication. Okay. And this minus also comes because we have minus here. We have minus here. Okay. Now I put them in the Newton's method for optimization. This is Newton's method for optimization. How here is the iteration index for Newton's method? This is inverse of Hessian. This is Gaussian. This is gradient. So gradient, we have gradient inverse of Hessian and this, right? This is inverse of Hessian. This is, by the way, guys, this is important. Why do we have plus here? In Newton's method, we usually have negative. Because you are maximizing the log posterior. We want to maximize the posterior. What was the posterior? P of label given x. I want to maximize this probability, the correct labels. This x given x, what is the correct label? I want to maximize this probability. Therefore, I have plus here, but where did this minus come from? Because there is minus in the Hessian already. Okay. And we repeat it until convergence of beta. We need to get used, I know, might be overwhelming, the calculation. But this is the routine in machine learning. All machine learning papers that you open, this is a routine. You need to get used to it. For example, I will not ask for proofs, but you need to get used to it. It needs to become easy for you. If it's overwhelming right now, you need to practice. All papers have these kinds of things. Otherwise, they will get rejected. Okay. Okay. So we train it. Several iterations. We train it. In the test phase, now test data point comes. In the test phase, what is the class of a point X? How do we determine it? How do we determine it? Recall the probabilities of classes. Let's go back and recall it. Go back, back, back. Equation 21 or 22. We calculate one of these. If you use equation 21, so put x in equation 21. If it's greater than half, what does it mean? It's in class 1. If it's less than half, it is in class 0. If you use equation 22, put x in equation 22. If it's greater than half, it's class 0. If it's less than half, it's class 1. Here, so we just take the threshold to be half of the range. This is logistic regression, as you see, can be seen as a one neuron of neural network for the sake of binary classification. Comparison to LDA. This is important. So logistic regression estimates d+1 parameters in beta. But LDA estimates many more parameters. I will tell you why. First off, why does it estimate beta D plus 1? What does logistic regression learn? What is the learnable parameter in logistic regression? Beta, right? We are optimizing for beta. What is the dimensionality of beta? D plus 1. That plus 1 is for the bias, right? So we only have D plus 1 estimations. Now let's see in LDA. In LDA, I told you, we fit a Gaussian distribution to each class, mean and covariance. Each class has mean and covariance. In a D-dimensional space, we have D by D covariance matrix, right? Therefore, we'll have D over D plus 1 over 2. D times D plus 1 over 2 parameters. Why? Why don't we have D squared parameters in covariance? So covariance matrix is D by D in D dimensional. Okay. How many parameters does it have? D squared, right? But no. Covariance matrix is symmetric. Half of it is enough. Number of parameters. So the number of parameters becomes D times D plus 1 over 2. Half of the triangle, okay, in the matrix. And we have two classes. Two of them becomes D times D plus 1. We have two classes, two covariance matrices. Also, each of the classes have a mean as a mean. A mean is D-dimensional. In D-dimensional space, mean vector is D-dimensional. We have two classes, 2 times D answers for mean. Also, they have priors, and priors are 1-dimensional, scalar. We have 2 of them, 2. Therefore, in total, we have 2 for priors, 2D for means, D times D plus 1 for covariance matrices, 2 covariance matrices. If you sum them up, it becomes D squared plus 2D plus 2. Compare this with D plus 1. Logistic regression estimates only D plus 1 parameters. LDA estimates D squared plus 2D plus 2. Much more. The simpler model, if we have 2 things which can explain one thing, Occam's razor. Occam's razor is this in logic and philosophy. You have 2 things which can explain one phenomenon. The simpler one is the better. I have said that in that lecture too that I recorded. Assume I'm hungry. There are 2 reasons. Either I haven't eaten for hours. The second reason, an alien came which was invisible and made me hungry. Both explain that why I'm hungry. Which one is reasonable? What's the first reason? That's the simplest reason. I haven't eaten for hours. Okay. So logistic regression outperforms in terms of number of parameters, LDA. And LDA also assumes the distribution of each class to be Gaussian. So assumes that the distribution of classes are Gaussian. Did we make such assumption in logistic regression? Did we make an assumption on the distribution of classes? We didn't. Did we? Did we say I assume the distribution of this class is Gaussian or whatever, Poisson or beta or whatever? No. So there is no assumption in logistic regression, there is no assumption on the distribution of data. However, LDA does that. So more assumptions and not good according to Occam's razor. Other history. So some history of neural networks now. In 1969, Arthur E. Brisson and Yu Chi Ho described backpropagation as a multi-state dynamic system optimization method. I told you about Perceptron, about McCulloch-Pitts, Perceptron, ADALINE, MADALINE, logistic regression. This is the rest, talking about the rest of the history. In 1969, they described backpropagation as a multi-stage dynamic system. Starting 1969, people started inventing and reinventing backpropagation. inventing and reinventing backpropagation algorithm for training multi-layer perceptron. What do I mean by reinventing? There are two ways that people reinvent something. You may invent some algorithm, another group invents another algorithm. At first sight, they might be different. But if you work out the math, you'll see they are the same thing. Described in two ways. Many papers are like that nowadays. They're saying the same thing. Okay, that's one way. Another way that at that time there was no archive and these things. There was no archive or there was no guys, please listen. At that time, guys, at that time, people could not read papers easily. It was hard. Okay, there was not. Therefore, maybe they were reinventing without plagiarism. They didn't know that such algorithm exists. So that's one. For training multi-layer perceptron. Why multi-layer perceptron? What's the reason? Why multi-layer perceptron? Because, as I said, perceptron was for linear classification. What they said for non-linear classification, their mindset was, let's stack several perceptrons and then we have multi-layer perceptrons. Okay. In 1972, Stephen Grossberg proposed networks capable of learning XOR function. Do you remember? Perceptron, the interest in perceptron was lost because it couldn't handle XOR nonlinear classes. Stephen Grossberg did it in 1972. In 1986, the main and successful backpropagation, which nowadays is used, was proposed by Rummel Hart and Jeffrey Hinton and Ronald Williams. That's why Jeffrey Hinton, they call him godfather of AI. He proposed the main backpropagation algorithm. There were several variants of backpropagation. The main one was proposed by Hinton et al. 1980s, successful era of neural networks. Successful time of neural networks, 1980s, was blooming. Then kernel support vector machines resulted in the winter of neural network. And it lasts years of previous century until around 2006. So let me explain this part a bit. Neural networks were blooming, but at that time, around that time, support vector machine came. And it said that, okay, I can find the best decision boundary for linear classification. I talked about it in this session, right? Also, however, SVM is just for linear classification. The authors said, I think one of the authors, as far as I remember, is Vapnik. Vapnik is one of the main scholars of machine learning. You can take a look at his papers, focusing on SVM, kernel SVM, and this. Okay, so they said they adopted the notion of kernel from pure mathematics, functional analysis. So functional analysis is a field in mathematics. Okay, they use that. Kernels were first proposed in functional analysis by Hilbert, as far as I remember. Yes, I think David Hilbert, as far as I remember. Yeah, Hilbert space. You have seen that. Okay, Hilbert space. Around what time? At the start of the previous century, when Einstein was alive, young. Okay, at that time. Later, physicists adopted that in quantum computing, quantum physics. So kernels were used in quantum physics later, in the middle of previous century. Then later, Vapnik et al., they adopted that from physics and functional analysis and brought it into machine learning. They used the notion of kernel in order to make SVM nonlinear. So the idea was that when we have two classes like these, which are nonlinearly separable, let's add the dimensionality to data. This is 2D. If I make it 3D, So I'm pulling the star class up. Then they become linearly separate, right, by a plane. You see that? So this was the idea of kernel SVM. Therefore, they could handle nonlinear data. Therefore, they were outperforming neural networks. Also, they were mathematically sound, like mathematics, theories, and proofs. Therefore, it resulted in winter of neural networks. At that time, at the end of in 1990s and the start of 2000, until 2006, there was winter of neural network. When people were submitting papers to NeurIPS conference and other conferences, they were getting rejected. Nowadays, it's the other way around. Nowadays, they are accepting more papers with neural network. At that time, they were getting rejected. Okay. Hinton had proposed Boltzmann machine and restricted Boltzmann machine in 1983 and 1985. Okay. During the winter of neural network, Hinton tried to save neural networks from being forgotten in the history of machine learning. Okay. So he returned to his previously proposed RBM and proposed a learning method for RBM with the help of some other researchers, including Max Welling. Max Welling is also one of the important scholars in machine learning in Europe. They proposed training the weights of BM and RBM using maximum likelihood estimation. They use maximum likelihood estimation for training RBM. BM and RBM can be seen as generative models where new values for neurons can be generated using Gibbs sampling. They use some sampling method named Gibbs sampling. And take a look at that later. In order to train, to make it generative model. So in other words, we have two layers of neurons connected to each other. They pass energy to each other. So there is a energy concept of energy in physics. These layers have energy. They pass back and forth. And if we have connections between all of the neurons, it will be Boltzmann machine. If we get rid of the connections between the neurons in the same layer, it will be restricted Boltzmann machine. Okay. So Hinton did that. And then Hinton noticed RBM because he knew that the set of weights between every two layers of a neural network is an RBM. But you can consider every layer of neural network as an RBM. Then it was in the year 2006 that he thought it is possible to train a network in a greedy way. Greedy way. What is greedy way, by the way? Greedy algorithm makes every decision based on the most benefit at the current step and does not care about the final outcome, hoping that at the end, the outcome will be reached. So I want to do something. I don't take a look at the whole path. At every step, I do what is best for that step. Maybe I don't reach to the global optimum. If I had looked at the global optimum, maybe my path would be different. But if I take every path as a local optimum, I hope that I reach to the global optimum. Okay, this is greedy algorithm. So in the greedy way, he tried to train every layer of neural network using RBM, where the weights of every layer is trained using RBM training. In 2006, it was published in Nature or Science, one of these two journals. The stack of RBM models with a greedy algorithm for training was named Deep Belief Network, DBN. Okay. Why belief network? Why is it called belief network? They called energy, the energy in physics that I had, the layers have, they called it belief. Because it's like that the neurons have some belief. DBN allowed the networks to become deep by preparing a good initialization of weights. So Hinton, what did he do in 2006? He said, let's not initialize the weights of neural network randomly and then do backpropagation. If we do that, we'll have vanishing gradients problem. Let's initialize it using RBM and then do backpropagation. It resolves the issue and we can make it deep. It was a breakthrough in neural networks. Okay. By the way, we will go through RBM in this course. This is just a history. Okay. For backpropagation, this good starting point for backpropagation did not face the problem of vanishing gradients anymore. Please wait a bit. We have time. Since the breakthrough in 2006, the winter of neural networks started to end gradually. Okay? Since 2006. Because the networks could get deep to become more nonlinear and handle more nonlinear data. And the problem was nonlinearity also and becoming deep. Why did they want to become deep? In order to handle nonlinearity better. Deep belief network, or DBN, was used in different applications such as speech recognition and action recognition. Right? Hinton was very excited about it and was thinking that the future of neural networks belongs to deep belief network. However, two important techniques were proposed. One of them was ReLU activation function, which we will see in this course in 2011. Another one was dropout technique in 2014. Okay. These two regularization methods prevented overfitting. Told you, please watch overfitting lecture. Okay. These two prevented overfitting in neural network and resolved vanishing gradients without RBM initialization. So we didn't need to initialize the weights using RBM anymore. We just could use backpropagation with random initialization. Hence, backpropagation could be used along if the new regularization methods were used. The success of networks was found out more by its various applications, such as image recognition. I remember at that time, a paper was proposed by some researcher in Stanford. Fei-Fei Li. Yeah, she is a researcher in Stanford working on computer vision using deep neural networks. Okay, Fei-Fei Li and her student, I think her student is now in Google. They proposed and they worked on a deep neural network which could completely understand what the image is doing. For example, the image was fed to the network, and an elephant was on a human was on an elephant riding an elephant in the image, and the network could generate that a human with red shirt is riding an elephant in this thing. Very shocking at that time. Because of these, the interest in neural networks again grew up. Okay. Some acknowledgements. For more information on early history of artificial neural networks, see this book. This book is very important, I think. Fundamentals of Neural Networks, Architectures, Algorithms, and Applications. It is an old book. It's not about deep learning. It is about ancient neural networks in the previous century, okay? Such as ADALINE, Perceptron, and these things. Some slides are inspired by teachings of Professor Ali Qudsi at Waterloo, Professor Fakhri Karay at Waterloo, and Professor Saeed Bagheri Shoraki at Sharif University. Okay. Some references, let's go through them. So this is the paper of McCulloch and Pitts, 1943. A logical calculus of the ideas immanent in nervous activity. This is the paper of Hebb. Guys, do you see how beautiful these are? 1949, the organization, this is a book by Hebb, The Organization of Behavior. This is the paper of Rosenblatt, proposing Perceptron, the Perceptron, a perceiving and recognizing automation project para in 1957. Guys, please listen. What was this one in 1996? I don't remember. You can take a look at the references in the slides. These perceptrons, this was the book in 1969 by Minsky and Popper, which said that perceptrons are not good. They can't handle nonlinear classes. This is the paper by Widrow and Hoff. For what? As far as I remember, ADALINE. This is for ADALINE in 1960. For ADALINE. This was, as you see, technical report in Stanford University. Guys, please don't speak, because when I say it's recording and your voices also will be recorded. So this is the paper of withdrawal technical report for the withdraw and half for ADALINE. This is another paper of ADALINE, an adaptive ADALINE neuron using chemical stores. This is also a technical report in 1960. Withdraw 1962 has another paper on ADALINE, the generalization and information storage in networks of ADALINE neurons. This is MADALINE rule 2. I think, as far as I remember, paper 8, I think, is MADALINE rule 1. We should take a look at that in the slides. So this paper 9 is MADALINE rule 2 in 1988. Okay, by Winter and Withdraw. This paper by Withdraw and Lair in 1990 for MADALINE rule 3. And if we take a look at the citations of this paper, it will blow your mind. Many people have cited this paper. It's an important paper. It's kind of a survey of what they have done in 30 years in Stanford for neural networks. Okay. Verhulst in 1845. I don't remember what this was for, but you can take a look at it. Walker and Duncan in 1967. Palmer, the origins of logistic regression. You can take a look for the history of logistic regression. You can take a look at this paper. And these optimal programming problems with inequality constraints in 1963. This one applied optimal control, optimization, estimation, and control. This Hinton, Rumelhart, and Williams in 1986. One of the most important papers in machine learning, proposing backpropagation, the main algorithm in backpropagation. See in Nature. Bozer, Guyan, and Vapnik. Do you remember? I told you Vapnik. Proposing kernel SVM. Do you know Lex Friedman?
Yeah.
He has an interview.
Yeah, science.
He has an interview with Vapnik. You can take a look at it. A training algorithm for optimal margin classifiers. I think this is related to SVM. Okay. In 1992, as I said, in 1990s, there was a winter of neural networks because of SVM, kernel SVM. That was for kernel SVM. Hinton and this in 1983. What is this? Optimal perceptual inference. I think this is for RBM, I guess, as far as I remember. Hinton and et al. In 1985, a learning algorithm for Boltzmann machines. This is also for RBM. As you see, Hinton was working on RBM in 1980s. Hinton in 2002, training products of experts by minimizing contrastive divergence. This is also kind of trying to recall RBM. With Max Welling, as I told you, with Hinton et al., they worked on RBM further in 2004, published in NeurIPS conference. Okay, and what this one was for? This is for Gibbs sampling, 1984, stochastic relaxation, Gibbs distribution, and the Bayesian restoration of images by Geman and Geman. This is the paper which proposed Gibbs sampling. Okay. Hinton and Salahuddinov, I don't remember what is it. This 2006. This is one of the most important papers in machine learning. This ended the winter of neural networks. Published in Science. This is exactly the paper which said let's initialize the weights of neural networks within RBM and then do backpropagation. Guys, please listen. Then Hinton and Teh, a fast learning algorithm for deep leaf networks in 2006. Again, see, deep leaf network and RBM were rising. And Benjo is now in Montreal, one of the important scholars in machine learning. Benjo et al., greedy layer-wise training of deep networks. See, at that time, people were starting to say, let's do it greedy-wise, because RBM is training greedy in a greedy way. Hinton proposed deep leaf network in 2009 in Scholarpedia. Deep leaf networks for phone recognition. It was used for speech recognition because Hinton was also interested in speech recognition at that time. Hinton, phone recognition using restricted Boltzmann machine in 2010. Hinton, also acoustic modeling using deep learning. See a lot of speech recognition at that time in University of Toronto. Who is this? Graham Taylor. Professor here in either School of Engineering or Computer Science, working on machine learning. Why is he a co-author of Hinton? He was a student of Hinton. He was PhD student of Hinton. Graham Taylor, Hinton, whatever, and Sam Royce. Sam Royce was one of the important scholars in machine learning, died, unfortunately. They used, so the PhD thesis of Graham Taylor was using RBM for action recognition. Modeling human motion using binary latent variables. In 2007 in NeurIPS. Bengio et al. Deep, what is this? In 2011, the paper which proposed ReLU activation function, which also said we don't need RBM anymore. Hinton et al. Proposed dropout 2 in 2014. So Hinton himself did something which stopped RBM also. Okay, these two papers, they said that there is no need to RBM anymore. Okay, so one of them was ReLU, one of them was dropout. This is my tutorial on overfitting and cross-validation, regularization, and bagging and boosting. I think it's very important for you to take a look at that. This LeCun, Bengio, and Hinton, they have proposed a paper on deep learning in 2015. Why is this important? It was the pre-publication because they were guessing that they will get the Turing Award. It was a pre-publication on deep learning because they were godfathers of neural networks. So they said, let's publish a paper in Nature about deep learning. We will probably get Turing Award. And they got, after years, they got Turing Award for deep learning. This Fei Li in Stanford, I told you, with Karpathy, her student. Karpathy is now in Google, I believe. This is the paper which I told you. It said that we can use it in computer vision very well. So at Stanford, people use neural networks for computer vision. In Facebook and University of New York, they use that because LeCun was in New York and also in Facebook. They use that for speech recognition. So use of deep learning in computer vision in Stanford, use of deep learning in speech recognition in Facebook and University of New York, they gained interest in neural networks. In 2015, this is the paper of elephants that I told you, and Fawcett, Fundamentals of Neural Networks. This is the book that you can take a look for history of neural networks. Okay, thank you very much.
Yeah,